Okay, I'm giving an update on Project Loom. For several JVMLSs, we've actually given updates on Project Loom, and this one is no different. I've tried to compress the material down to 45 minutes because there's so many different parts to this project because it touches so many parts of the JDK. So we will spill over, I think, into a workshop later on. Okay, so for today, we're actually just going to, for this session, I'll just give an update on where we are on virtual threads. We've had pain points around pinning and object monitors that we're going to spend time on. We've had pain points around troubleshooting and building out the story around diagnostics and serviceability. So I want to talk a bit about that. So from troubleshooting to troublemakers, we've got the people that want to replace the scheduler. So I want to talk a little bit about some of the exploration that's been going on that. And then we have two APIs that we have in preview for a couple of releases, structured concurrency and scope values. I'll just give an update for the recording of this session so that there's a good understanding of where we are on these APIs, and we'll talk more about it in the workshop today. Okay. In order to get into this, I'll just quickly explain where things are at a high level. I want to explain a little bit how virtual threads actually work, because many of the slides that I'm using just build up some pictures based on just the initial understanding as to how things work. When we were here last year, we were just at the point of actually making virtual threads a permanent feature. That actually happened in JDK 21. So finally, after 5 or 6 years of work and iterations, the feature finally became permanent in JDK 21. Very well received from the ecosystem, huge amount of frameworks, libraries, added support for virtual threads, even before we actually GA'd, so that was actually quite good. The main thing we were actually seeing is a huge interest in using virtual threads for very much highly scalable concurrent applications where you can actually represent every concurrent task as a virtual thread. That's actually really cool. It means you actually move away from the spaghetti that was async code and callbacks and reactive. So that's the main thing is making code a lot more readable, easier to debug, easier to understand. So I think we've actually succeeded on that front. Overall, the performance has actually been quite good. Reliability has actually been quite good. Even though there's a lot of people using this, there's actually been very few really serious issues actually come up, and those bugs actually did get fixed quickly. However, there are a few pain points, and as we talked about here last year, is we had to make some decisions when we went to make this a permanent feature on what things, to avoid having to delay this feature another 2 years in order to fill out these other pieces. We actually decided to move ahead. And that's what I want to talk about today, because these things are showing up as pain points. So just a reminder, and we've seen this in a couple of presentations here over the years, and there's a deep dive on this exact topic from last year's JVMLS where Ron Pressler went through exactly how all of the magic that goes on in the VM in order to support this. But at a high level is virtual threads are really just a combination of delimited continuation implementation in the HotSpot VM, and we're combining it then with a fork join scheduler. So the two things actually come together in order to build a thread library in the Java language, which is quite interesting. So a virtual thread essentially just wraps a continuation. Continuation gets executed. When the task that's running in this virtual thread wants to block for some reason, for example, on a lock or on a socket, whatever it might be, then the continuation yields, and that frees up the thread to go and do something else. And when it's actually scheduled to continue again, the continuation is run again, and that causes is continued. So that's sort of the high level. Most people here that will have seen presentations on this over the years. So the scheduler that we're actually using is based on Doug Lee's fork join work stealing scheduler. For parallel decomposition and on those other sort of traditional tasks that work stealing schedulers were used, it's configured in very much a LIFO type of mode. What we're using it here is more kind of a FIFO mode, and that's presented a few challenges over the years and why the fork join is iterated, and there's been quite a few updates in the JDK over the last few releases, basically to cover the scenarios that we need to optimize for here. The way the scheduler is set up is parallelism is just defaults to the number of hardware threads, And we have a little bit of dynamic up and down where target parallelism can increase and decrease as depending on the execution. I want to show some of the examples and some of the pain, and in order to do that, I actually just have to give a quick, brief 5-minute tutorial just on how things actually work. So the way these slides are actually structured is I've got the code on the left. So this is Java code that's going to be executed by some virtual thread. And on the right, I'm actually going to throw some thread stacks. In these presentations here, typically people come along with lots of code examples. This presentation comes along with different stack traces, whatever. Okay, so what we have on this example is, I'm just going to use a semaphore for this, which is very simple. A semaphore has a number of permits. It's got an acquire and release to acquire a permit and release it back. You typically use it in a structured way in a try finally. So let's see what happens when we execute this. So hopefully the slides are actually clear on top. There's actually two colors here. The yellowy brown, I'm not sure how it comes up on the screen there, that is our carrier thread. There's 2 thread stacks that are shown on this slide here. On the top is our carrier thread. This is our fork join thread that's actually executing it's our scheduler. And what we have done is we have mounted a virtual thread on top. The frames that you actually see there in green are the virtual threads stack. So what happens is the virtual thread is coming along and it's actually going to call semaphore.acquire. That's where we're actually going to attempt to obtain a permit. If there's no permits available, what happens? The thread has to go and park in some way. So we'll actually see, once we actually expand the stack, we'll actually see is it goes down through the implementation of semaphore. That goes down through the, in Java Tool Concurrent is sort of the underlying framework there is an abstract queue synchronizer. Goes down through all of this code and bottoms out in a park method where the thread actually has to go and park. When a virtual thread attempts to park, that actually just causes a yield on the continuation. And this is where the magic happens, is the stack frames just get copied away over into the heap. In VM terms, this is a freeze operation. And as I said, Ron's presentation from last year has all the gory details and magic that makes this really, really efficient. Because we're not actually copying all of the stack frames all the time. There's a lot more interesting things actually going on there. So the stack frames have been copied away over to the side. We've left just now with the code that's running now in the context of the fork join carrier thread. And it's now going to, it's now freed up to do other work. And that's the sort of the basis of how it works. So sometime later with a semaphore, if there's no permits available, you basically go onto a queue waiting to acquire a permit. And some other thread is going to kindly release its permit and call a semaphore release. So I'm not saying whether this is a virtual thread or a platform thread on the right. It's just some other thread that happened to wants to release a permit, and it will go down through the semaphore queue, the semaphore code, and select a thread to be unparked, and it actually calls the unpark method on that thread. And for a virtual thread, that ends up queuing the task for that virtual thread back to the scheduler. So that's what happens is now when our scheduler schedules that virtual thread to continue, all of these stack frames that were copied over on the side conceptually are copied back onto the platform stack. Remember, it's optimized. It doesn't really do all of this. So we're back to where we were a couple of slides ago, where all our frames are there. We're still in semaphore acquire. And we move on, and execution continues. And now we're actually in the try finally block after obtaining a permit for the semaphore. So at a high level, how this all actually works, and I'll go through a couple of slides in a minute, just that uses exactly the same format. Code on the left, stacks on the right, same color code, so you can actually see what's actually going on. Okay, so in JEP 4.4, which is the JEP where we made virtual threads a permanent feature, we have some little, I'm going to read this slide. There are 2 scenarios in which a virtual thread cannot be unmounted during a blocking operation because it's pinned to its carrier. So when I say when we say the word unmount, what we mean is that we actually, in the blocking operation, we can actually copy all these stack frames over, free up the carrier thread to go and do other work. So we've got two scenarios. One is when it executes inside a synchronized blocker method. And the second thing is when we actually have a native frame on the stack, because we can't deal with arbitrary native frames. I'm just going to read the last line. So pinning does not make an application incorrect, but it might hinder its scalability. Well, okay, we could actually say a lot more than that, because as over the last year or more, people have run into this quite a lot, because there is a lot of code over the last 25 plus years that's using synchronized, and people are actually running into some scalability issues here. Some people have run into kind of starvation type of issues, and even deadlock when all of the carriers actually pinned for some reason. So this has actually become, this one here was sort of been our kind of number one pain point for the last while. We talked a little bit about it in the workshop last year. So if I was to summarize, so one of the things about having a feature out there for quite some time, if you attempted to actually summarize all of the feedback that we got on this particular issue, is you can kind of sum it up as one word, sort of ARG, which is because people are actually quite frustrated at this one. So we actually have to go and deal with this issue. So let me explain actually what actually happens with object monitors, because it's actually not just one case, it's actually three cases. So if I were to park while holding a monitor, so in this example here, I'm actually going to park, I'm going to attempt to read from an input stream. The input stream is actually backed by a socket, so I'm actually going to be reading from a socket. So on my right, I have the carrier frames as before. We're now in this virtual thread, and it's going to attempt to do a socket read. What happens with a socket read? Well, a socket read is actually going to arm the file descriptor, and the thread is going to park. But when we start bottoming out on the yield fails. Why does the yield fail? The yield fails because we're actually in a synchronized block in this particular code. So what happens when yield fails? What is the parking code going to go and do? It's going to park on the carrier thread rather than actually exposing an exception or causing the socket read to fail. So it'll temporarily park on the carrier thread. So I'm using a little pin icon here just so in these slides you can actually see where we're pinned. So when we're pinned, it means that we cannot release the carrier to go do other work. So you end up with a scalability issue here. So that's number one scenario, is where we actually attempt to park while in a synchronized block. Another, number two then is where we get contention on a monitor. Someone else actually in this particular case is they are in they're owners of this lock here, OBJ. I come along in a virtual thread and I attempted to do a monitor enter. I get pinned at this point. I cannot release the carrier. That's really, really disappointing. We also have the third scenario then, which is object.wait. So most of the scenarios we've seen over the last year tend to be of the type where people are blocking while holding a monitor. Seen less with the contended monitor, and even less again with people using object.wait. So these block within the VM. So that is why we have pinning issues with object monitors. So what can we, well, let me first explain why do object monitors cause pinning? So here you just have to sort of give a summary as to the way things work within the HotSpot VM. So there's sort of two locking modes. This first one is this stack locking or legacy mode, locking mode as it's called now. What it actually does is that it when an object gets locked, there's a lock bit gets set, and the header ends up pointing to this lock record in a Java frame. So the lock record ends up pointing back to the object. So you're actually pointing to something in the Java stack. So that's actually very, very problematic, because if a virtual thread were to unmount and you've got this object that's got a pointer back into the lock stack, back into the Java frame of the carrier, you're going to end up with an invalid pointer. That is actually not going to go and work. Thankfully, this locking mode is actually is sort of going away. It's deprecated, and everything since JDK 23 is defaulting now to this lightweight locking mode. Roman has talked a couple of sessions. I think last year you did a good session on some of the pre-work for Lilliput, And one of this was actually revisiting the locking modes. And then with this lightweight locking mode, which is a default since JDK 23, there's this thing called a lock stack. And I think you probably, people here would have seen some of the slides where there's this little, I think it's like eight oops or eight entries in this little lock stack. And a monitor enter is a push to that stack. A monitor exit is actually a pop. So it's a very small little stack that actually ends up spilling. We'll get into that in a second. So this actually turns out to be a little bit simpler for virtual threads. We do a push and a pop, but we cannot unmount while we've actually got while a virtual thread has actually locked something that's in that lock stack, because if it did, you totally confuse the ownership. If we were to actually copy the unmount, it's as if the carrier now owns this lock that the virtual thread actually acquired. And if some other virtual thread were to go and mount, then you confuse ownership even further. So this is a problem. And then aside from those locking modes, you've got this sort of heavyweight inflated case where these things go to this object monitor structure in the VM. And it's got its own issues there because it has some notion of ownership. And the owner is actually a Java thread thing that's actually in the VM that's actually tied to the carrier. This is not something we see in the Java heap. This is something that's in the native heap. So that would confuse ownership even more, because it would appear again that something has been owned by a carrier thread. So this is a problem that has been known for quite some time, and so all of these issues here are why the implementation currently is forced to pin. The way it does that is just by keeping account of the number of monitors that are actually held, and it causes the freeze then to fail if you're actually holding a monitor. So that is just explaining why the pinning issue is actually there and why these freezes are failing. Then we have the contended monitor case and the object monitor case. Both of those, at least is the way they work in the main line is they actually block in the VM, and they block on the carrier, thus pinning the virtual thread. So this is problematic, as I say, for scalability and other reasons. So when we were here last year in the workshop, we were talking a little bit about possible directions on this. And there was a project running at the time, which was called Java Object Monitors. Robin Ian was actually running with this and actually had got it so far where he had actually re-implemented monitors in Java. He had the interpreter working. And so there was some green shoots there for a direction to replace what we have now with a new implementation of object monitors. But there was a lot of work to do in this. And lots of unknowns, because as soon as you start re-implementing some of these things, parts of the VM in Java, you end up then grinding with all the other interfaces that have got added over the last 25 years. So a lot of challenges, a lot of unknowns, and a huge number of person years of work would be required to re-implement monitors, because there's going to be so many other issues that are going to come out of the woodwork. Since then, the other option appeared on the table, and we can thank Patricio Celano Matteo for this in the HotSpot runtime team. He was doing work on some of the force preemption that we had in the prototype, and made some observations that the existing object monitor implementation could be adapted to work with virtual threads. And that work has been happening over the last year, and I want to talk a little bit about that. So what he's been able to do is essentially get the existing implementation of object monitors in the VM to actually work with virtual threads. The way this works is it's at this point in time, it's only the lightweight mode. So a couple of things kind of came together in our favor. The work on lightweight locking went in as experimental in JDK 23. I think folks on the GC team addressed a lot of the performance issues, particularly around some of the reentrancy and large number of locks. So that has been improved and became the default then in 23. So this is nice because this is a lot simpler. This is their little lock stack. So the implementation that has been done is solely for the lightweight locking mode. We don't care about the legacy locking mode because that's now deprecated and I think will be going away. So when I talked earlier about is the mounting and the unmounting is doing the continuation yield and that's causing, at least conceptually, all of these frames to get copied into over into the heap, into this sort of GC managed object for all these stack chunks. This is now amended to additionally freeze the lock stack. So these entries that are on the lock stack, as part of the freeze operation, they also get copied over into the stack chunks. When you actually continue and you do a thaw, at least on the first thaw, that lock stack can come back in from the heap and get restored. So that actually is conceptually very simple and works quite well. The other thing that has come in our favor is, at least in Project Loom, is we've doubled down on the thread identifier that got added back in JDK 5 in order to be able to support monitoring and management. But we've actually been able to use it for quite a number of other things to identify virtual threads as part of other work. And this lock ownership issue, which I said was pointing to this native data structure, is now changed in this implementation to not use a Java thread, but use the thread ID, which is basically a 64-bit pointer. So that's actually nice because there's nothing to go and fix up. So that's actually really, really simple. In addition, as part of other work that was going on in JVM-TI, we removed some of the problematic cases going from thread to what objects are owned, what locks are actually owned. Those kind of questions that require you to go from one object to another. Some of those questions and needs disappear with some of the other work that has gone on with JVM-TI over the last couple of releases. So that's actually really, really good. So a lot of things actually aligning there, which is nice. The other thing then so that addresses the issue that we have with the being able to block inside a synchronized method or synchronized block. Then we have the other issue of the monitor enter and the object wait. So Patricia did his magic here on monitor enter, and this is now making use of preemption that's initiated by the VM rather than initiated from Java. So this is actually, so we've always had to initiate the yielding from Java code. With the work that's done here, it's initiated from the VM. So when we go into monitor enter, it's contended. We're able to add now the virtual thread to the queue. There's a CX queue in the VM for queuing the threads. It gets added there, and then with a bit of magic and some preempt stubs, control then can actually return back up, and we can actually complete the unmount and do all the state transitions that we need in order to be able to do the mount. So that's actually really, really nice. It means that we get preemption at monitor enter. When we come to monitor exit, this is now actually changed so that if we're actually going to go and release a virtual thread, then there's now a mechanism to be able to queue that virtual thread back to the scheduler exactly like we had with the semaphore release in one of the early slides here. There's a little bit of performance work is still being fleshed out on this, but essentially is that the virtual thread can be queued to be unparked, and then it actually goes and competes again to re-enter the monitor. The performance work that's going on there is mostly that a thread calling monitor exit is that sort of in HotSpot parlance, it's actually a leaf method. We somehow need to be able to integrate then with a scheduler that's in Java. How do you actually do that up call? At the moment, it's done by means of queuing it to this other thread that does the unblock. But as it happens, and so many things actually align to make all of this happen, is as part of the prototype Java object monitor work, there was already some compiler work around this already that provided some direction as to how this could actually be fixed. So that work is being worked out, and that will hopefully address the performance issue around that. Object wait is kind of similar, so sort of it's a different wait list, but it kind of works the same way as contended monitor enter. So that's really, really nice. So all of these things combined gives us a solution for the three scenarios that I went through. So holding a lock, remember this is a slide that I had earlier on. We arm the file descriptor, we attempt to yield. Now what will happen is the yield actually works. We release the carrier to go and do other work. Great. Monitor enter. The monitor is owned by someone else. Now we actually get our preemption. We release the carrier to go and do other work, which is great. Object wait, exactly the same thing. We were able to release the carrier and do other work. So all good. Right. High-level summary on where we are on this is the changes for this have been accumulating in the Loom repo over the last number of months. We've had early access builds, I think starting back in March as the pieces were coming together. There's quite a few people actually trying this out, which is great, including some people with some large stacks. This actually is pretty good in terms of reliability. We've got one performance issue that I mentioned that hopefully will get worked out. Because of the significance of the changes and because there is a lot of interest in this topic, we've drafted a JEP for this, and we want to submit this soon to get it onto the technical roadmap and hopefully propose this and get it into JDK 24. And that should hopefully address the pinning issues that have caused so many issues over the last year. Right, now we actually have to ask the hard question. So you've addressed object monitors. Are we done with pinning? Well, not quite. There's a few other things that are going to come out of the woodwork. They will be less of an issue, but they're things that are going to come up. A big problem we have that is executing code, and we have to resolve a constant pool reference to a class or an interface. What happens is you end up calling into the VM. You may have to do class loading and run a class initializer. This is being done with a native frame on the stack, so it's very problematic. You might say, oh, class loaders aren't going to go and block, or static initializers aren't going to go and block. Well, I was looking at a stack trace recently, and it was over 1,000 frames. We were trying to figure out why is it pinned. I borrowed a ladder from my neighbor because the stack trace is so big I couldn't see it all. Way down in there somewhere, close to 1,000 frames away from the blocking site, was actually a sealant method. A static initializer had caused a huge amount of execution and caused the thread to block. So these kind of things are actually problematic. More so is going to be waiting for class initializers. So the way the VM spec works is that there's one class actually executing, but then other threads that come along and they attempt to reference that class, they're actually blocked waiting for the class to be initialized. What we've actually seen in some scenarios where you actually get a storm of threads that are going to execute essentially the same code. And in highly concurrent applications, that would be sort of somewhat typical is a large number of threads are going to execute the same code. They're now all going to get queued up waiting for the class to be initialized. And they're waiting inside of the VM with this non-visible mutex locker that's actually inside the VM. So this is probably something we actually have to go and address once we get the work for 24 out of the way. And this is actually kind of an interesting one to address anyway, because class initialization lock has been a pain for the ecosystem for 20 plus years, because it's not something that's exposed by serviceability. It's not a Java object that the tooling and profilers can actually deal with. So that's the main thing that we'll have to look at once we get the object monitors out of the way. There's a couple of other little random things around the place. If you've seen the Stackwalker API, Stackwalker API calls through a native frame, so that's going to be problematic if you're actually consuming your own stack trace with that native frame on the stack. There's a few other things that have come up in Graal's truffle framework. They're calling through JVM CI, that's compiler interface, and that's a native frame. So things like this will come up, but less so. This will be nothing compared to the issues that we have with object monitors. Okay, so that's other. I'm mostly bringing good news in this presentation, but there's other pinning issues, so there's a little bad news that sort of balance that out. All right, okay, so the next thing I want to talk about is troubleshooting, because this has come up. I don't know how many people have written articles over the last year about some of the issues that they've had with troubleshooting. So we've had 25 plus years of building out serviceability APIs. A big advantage for Java and the VM has been just the amount of serviceability, observability, diagnosability, something abilities. Because we've got APIs, we have tooling, we have a whole bunch of stuff that has built up in the ecosystem. So there's sort of an expectation is, oh, all of this stuff worked for 25 years with virtual threads, or sorry, with platform threads. Surely it's just, this is just a thread, everything is going to work with virtual threads. Well, maybe, we'll see. So one of the things I like to think about with virtual threads and diagnosability is, what are we competing with here? You're not necessarily, virtual threads aren't necessarily competing with platform threads, because it'd be silly just to go and replace platform threads with virtual threads. You're actually providing something that allows people to move away and avoid having to use async and reactive and all that other maintainable code. The VM and the Java ecosystem has close to zero to support those type of applications. So I think we're actually competing with something that has nothing. So that is, if we even provide one method to provide a thread count, we're actually better than what's there for async. So where we were, we have actually been working on this for quite some time. So even what we brought into JDK 19, 20, and 21 has actually been quite a lot of the pieces that go with diagnosability. We spent the serviceability budget twice over getting the debugger support in there. JVM TI is this huge big surface area of 150 plus functions and a zillion callbacks. And getting all of this to work in some way with virtual threads was a huge amount of work. So IDEs, debuggers, all of this stuff just works with virtual threads, which is really good. The JFR folks did a really, really nice job getting JFR events to be able to be recorded with virtual threads. So that is actually quite good. New diagnostics were added from the beginning to help detect the pinning issue. So we introduced this problem of pinning, but we also give you the tool to actually detect that pinning. So the several features went in there. Thread dumps is an interesting story, because HotSpot thread dumps are very much stop the world. Here's a snapshot of all threads. That's not necessarily the right thing when you've got 1 million virtual threads in your heap. You don't want to stop the world and actually go and grovel through the heap to go and, so we to produce a thread dump. So we did something else for this. We produced a different type of thread dump that gives you sort of a weekly consistent view of the different groupings of threads. More work is required in this, but it actually gives you a nice view of all the threads of execution, and it's actually parsable. So tools outside of the JDK can parse this. They can do deduplication. They can do all their queries on this. So that's actually quite good. Some work has happened in the meantime. The heap dump support was actually wasn't great in 21, but it actually has improved now, so that the heap dumps actually can include virtual threads and the stack traces of unmounted virtual threads, which are some of the challenges that we had in this area. So there's a lot of other things been happening. The HotSpot thread dump is now expanded out to be able to actually include the stack trace of mounted virtual threads. Good for detecting pinning, good for actually detecting people that are actually computing pi in the context of a virtual thread. So all of those kind of things that people were looking for are added to the thread dump. We've actually expanded all of the JFR events in this area. So I said we had JFR events and diagnostics for pinning, but it was actually only in a limited case. So this has actually been expanded out now to be able to cover other scenarios. So I'm doing object wait, but there's a native frame on my stack. I'm now going to get a JFR event recorded. Same thing for contended monitor enter, waiting for class initializers. All of this has actually been expanded out, which is nice. We've started building out some other tooling. So okay, there'll be a bit of bike shading and some of the names on this. But we've now have things set up that we can actually expose through a J command a whole bunch of things. What we'll bring into the mainline, not exactly sure yet, but we can actually get a dump of the thread groupings, thread counts. We can actually look at the default scheduler. There's a whole load of information you can actually see on that. We actually use a number of timer queues and be able to support virtual threads do timing. Some of that's going to get replaced over time, but at least we've got observability into that now. We have put in hierarchical polling mechanism in JDK 22, so there's a lot more sort of spreading out of file descriptor arming across different pollers. You get visibility all of that too. So a lot of good things are actually happening on the diagnosability side of things, But there's a lot more to do. You can actually spend several more man-years of work on observability and serviceability if you wanted on this area. So the main thing that we're still actually missing is we have to provide some consistent views of threads and locks and monitors in the thread dump. So that's one of the things we have to work on next in this area. We're getting there. So starting with very little, but it's gradually improving. I don't think we'll ever end up with the full gamut of features that we have for platform threads. We'll get the things that people actually need for observing highly concurrent applications. Okay, I want to talk a few minutes about the schedulers, only because this project has been spending a bit of time over the last year on this topic. So remember, I've used this slide several times. You've got 1 million virtual threads. They're basically sitting on this small pool of platform threads called carrier threads when virtual threads are mounted. There are people that find it interesting that there's these little threads in here, and they're very much tempted to come along with their own threads, with the go faster stripes, and replace those threads with their own threads. And they've got particular reasons for doing this, and we actually had exposed in a mechanism for doing this in some of our early builds. We didn't bring it into mainline, but we wanted to do some experimenting on this. And now these experiments are being dusted off again. So I just wanted to give an update on this and maybe set some expectations around this. So there's two kind of efforts exploring. I don't know where Andrew Haley is he's got one team that's in Red Hat looking at this, and then there's the folks in Oracle working on other exploration. Okay, so there's one group of folks that they've got their existing server applications that are all at their core is event loops, because that's very, very highly efficient. So they've got an async core, and then they're trying to integrate it with virtual threads. So there's some kind of handoff actually going on there, and doing a handoff from one event loop thread to a virtual thread that's sitting mounted on some other carrier. That's something that they potentially want to optimize. So the API that we had exposed on an experimental basis, that has been dusted off for people to go and try. Not necessarily something we want to bring into the mainline at this particular point. No decisions on that. But we want to actually get more feedback on it, because this was in our early access builds for more than 2 years without getting much feedback on. So we will see what actually will come from that, what kind of performance experiments will actually be done, and whether this is something that should be explored further. The other exploration is the people that have actually accumulated over the last 20 plus years their own thread pools. And they've got their own dynamic thread pools where they're able to actually monitor task queues and do all sort of adjustments. And then they try to convert this over to virtual threads, and it doesn't perform as well, particularly under certain workloads. So work stealing works really, really well with virtual threads on a busy system. But when the system is not under load, what are these work stealing worker threads going to go and do? They're actually going to be looking around the room and finding work to do. And those things before they actually go and park. And that little bit work spent looking around for other work to do is observed as additional CPU usage. So it's like, oh, this is regressions. This is using up more CPU time. So anyone that actually has built up performance models and is doing extrapolation from any of their existing workloads and benchmarks, they see a difference here. So these folks have been experimenting with coming along and replacing the fork join pool with their own thread pool that they control themselves. So they can do their own dynamic number of worker threads and so on. We'll see what actually comes from that, because when they magically replace the thread pool, then they get exactly the same performance as they did before, because they haven't changed anything significant in the architecture. Okay, so one last slide on this is that so we had explored this space up to a point in the Loom repo, but we didn't necessarily explore the full problem space. There's a lot of issues having a scheduler being run at very critical points in the execution and calling out to this arbitrary code that's owned by some server application over here. that's something, it's too easy to deadlock. There's too many other issues that can come from that. So we have to be somewhat cautious around this kind of thing. The API that we had on an experimental basis was very much a very simple API, allowed schedulers to attach context and so on. There's a whole bunch of other things that we knew would be needed in a fully API for schedulers. And we haven't done any of that yet. So there's a lot more thinking needs to be done before we go anywhere on this. So main thing on this is that there's explorations going on. It's from different folks in Oracle, different folks in Red Hat, middleware folks, because they like doing this kind of replace the scheduler. But we will have to see where this goes. But this is something we have to be very, very cautious on the platform because it could end up being an attractive nuisance. Okay, I want to move on and just quickly give a summary on structured concurrency and scope values. So structured concurrency is, we went through a number of slides on this at JVMS last year. So I'll just read out where we had on JEP 480. Structured concurrency treats groups of related tasks running in different threads as a single unit of work, thereby streaming, error handling, and cancellation, improving reliability, and enhancing observability. Quite a mouthful in there, but the main thing is that at a high level is we're actually, a task is split into a number of subtasks, and they will reliably join before the main task actually continues. And we have cancellation in there to be able to deal with reliable shutdown and ensuring that you're not leaving any threads behind. And this is actually really, really hard to do with everything we have in the JDK. There's so many problems that where you end up waiting for something, but the other your sibling task has actually failed and so on. We went through some of these examples last year. Okay, so this API has been in preview since 21. I think one of the challenges we have generally with preview APIs is trying to get feedback, and I think part of it is people are concerned APIs change, but and they can do when they're in preview based on feedback. So it's been hard to accumulate feedback, but we have a few things that actually came up is people pointed out a few issues, usability issues with the API. There was one or two little hazards in there. I think the way this API, so this structured task scope is something that Brian, Ron, and I came up with when we went through all of this originally, is this API was designed to use subclassing to implement policy. And we had the JDK then ship in preview APIs with two different policies. People found that a little bit surprising that you'd actually use subclassing for this. And there are a few issues that actually come from that. In particular, it puts constraints on the base implementation for evolution. A few questions come up around where does business logic go, how I deal with correlation, especially when my tasks are lambda expressions, and so the task identity isn't all that good. Where we ended up with deadlines and timeouts wasn't exactly where we probably should have been. The people wanted actually the timeout on the entire block. So these are the type of things that actually have come up since JDK 21. So Victor Klang and I have actually taken another stab at this. We went through all of the different use cases. We explored various different API shapes. We've gone through several different prototypes to explore different types of APIs. One of the things we can't lose sight of with this API is it's very much an API about providing a gentle on-ramp to structured concurrency. It's very easy to fall into the trap of just producing something similar to the invoke all, invoke any combinators that you'll see in executor service. So they just look like utility methods, these combinators. And that's not something we actually want to teach people. We want to actually teach people around about forking subtasks and doing a single join. So there's only a single barrier within the block. So that's something we have to continually remind ourselves without in doing these APIs. So we've come up with a new iteration of the API. It's not significantly different in terms of shape, but we've a better story for plugging in policies. We've addressed some of the pain points and hazards, And so we can talk about a bit about that. So we are going to re-preview this API in 24 because it's not a massive change to the API, but it's a change to the API, and we don't have the confidence yet to be able to make that a permanent feature. So scope values. So scope values, I'll just read out what we describe in the Java doc, a value that may be safely and efficiently shared to methods without using method parameters. So it's a bit like implicit parameters that you see in other languages. This API has also been in preview since 21. A little bit of feedback, but not a huge amount of feedback. We did an API change in 23 to address some of the usability points with checked exceptions. There's another API change that we want to do in 24 in order to be able to just make it a bit more usable. But overall, I think we're actually happy at this point with the shape of the API. There's still a number of performance optimizations that have been left on the table that we'll have to come back to. I think TBD, and let Andrew talk in the workshop later on today about this as to whether we want to move this forward as a preview feature or make it permanent. We still have to decide on that. And that is it. So these are the links to the JEPs that are there. As I say, we will have new JEPs that we hope to get proposed for 24 for object monitors, re-previewing structured concurrency and scope values. And everything that we're working on is sitting in the Loom repository. So that is all I have. All right, thank you.